the Instituto Politécnico Nacional of Mexico welcomes you. Today, we begin with the high-frequency electronics talk sessions in the frame of the Institutional Chair Eugenio Méndez do Curro, 2020. The sessions of today are entitled High-Frequency and Terahertz Devices and Circuits, Perspectives on Emerging and Advanced Technologies, Part 1. We are sure that these talks will be very fruitful to the audience, and we thank the speakers and the public to attend this event. These talks will be held in English. El Instituto Politécnico Nacional les da la más cordial bienvenida. Hoy comenzamos con las pláticas de electrónica de altas frecuencias en el marco de la Cátedra Institucional Eugenio Méndez do Curro de 2020. Las sesiones se titulan Dispositivos y circuitos de altas frecuencias y terahertz, perspectivas de tecnologías emergentes y avanzadas. Parte 1. Estamos seguros que estas pláticas serán muy fructíferas para la audiencia y nosotros agradecemos a los expositores y al público por estar aquí. Debido al nivel internacional de estas pláticas, estas serán dadas en inglés. Muchas gracias. Now, Dr. Elena Acevedo, go ahead, please, with the first speaker.
Thank you, Dr. Eloy. Well, our first speaker is Dr. Pedro Carlos Feijoo. Dr. Feijoo obtained his BSc degree in physics and the MC degree in applied physics with a specialization on electronics from the Universitat Complutense de Madrid, UCM, Spain, in 2007 and 2008, respectively. He obtained his PhD in physics degree from the UCM in 2013 in the field of microelectronics fabrication. From 2014, he has been working in simulation of microelectronics devices based on two-dimensional materials at the Universitat Autònoma de Barcelona, Spain. He has done internships at IMEC in Belgium and Alto Yliopisto in Finland. Welcome, Dr. Feijoo from Universitat Autònoma de Barcelona. Our speaker will present the topic, the theoretical limits of radiofrequency performance of graphene field effect transistors. Doctor, you have 30 minutes for your exposition. After this, we will have a question session of 15 minutes. Please, all the questions go to the end of the exposition, and the questions should be written written in the chat. And I'll pass the questions to the speaker. Dr. Feijoo, please start your presentation.
Okay, thank you very much for your presentation. I will start sharing my computer. Okay, I hope you can already see my presentation. So I'm going to present this, as Dr. Elena Acevedo has said, the theoretical limits of radiofrequency performance of graphene field effect transistors. I would like to take the opportunity to thank the organizer of this conference for giving me the chance to spread the research that we do here at the Universitat Autònoma de Barcelona. So this is the outline of my presentation. I will start with the introduction, where I will try to justify the research that we do in the field of graphene. Then we will pass to the simulation, to the model that we use to simulate the different graphene field effect transistor at its performance. And then we will speak about the comparison between our models and some experimental work that is done by a group that collaborates with us. Then I will pass to some results that are a summary of how the different parasitic parameters parameters, the parasitic parameters, how it affects the performance of the graphene field effect transistor, and finally I will extract some conclusions. Okay, so let's start with the introduction. Since its discovery in 2004, well, the discovery that it was stable at atmospheric pressure and so on, the graphene attracted a lot of interest in the field of microelectronics, since it has a very high mobility and a very high saturation velocity, as you can see in the presentation. In fact, if you compare the numbers of graphene to the ones in silicon, that is the material where all the electronics is currently based, you can see that the electrons inside the graphene are much more quick, are much more fast than in silicon. So this would mean that the devices made of graphene could achieve to higher frequencies than silicon. In fact, the main important thing in graphene could be to reach the gap that is above the radio frequency. As you can see in this image, let me show you, below the terahertz regime, there is the radio frequency that is used in telecommunication, and above there is the visible light, where the photonics takes place. But in the middle, there is a gap that could be of use in the graphene technology. And why it is important to reach this gap? Because it has some very important opportunities that would be good for some fields like medicine or security or so on. Okay, and why didn't we use this region of the spectrum before? Because there were no any device that could be able to use it. So there were necessary some new materials to reach this gap, and graphene is one possible choice. Okay, and how do we measure the high frequency performance? So imagine we are going to use the graphene inside transistors, and this would be a typical structure of the transistor with a gate and a source and a drain terminal. Remember that the voltage that you put at the gate controls the current that goes from the source to the drain. Okay, there is a fourth terminal, but we are not going to care about it because it is kind of a reference terminal. So the most important ones are these three. And when we are talking about high frequency performance, what we do is to use the transistor as a two-port network. A two-port network, we use the source terminal as a source, as a reference, and then we introduce a signal at the gate and we get an output at the drain. Okay, so what we are going to do is to use this kind of a scheme. We will put a signal at the input, and then we will get an output. And what do we care about this? What we need is to maybe to multiply by a factor to increase the factor of the current that the ratio between the drain current and the gate current, or to increase the power. So what we are going to analyze about these transistors is the possibility to use the current gain and the power gain. Okay, and how can we measure the current gain and the power gain? What we are going to use is the figures of merit of high frequency performance. When we attend to the maximum current gain, we define the cutoff frequency as the frequency that gives us a current gain of 1. On the other hand, if we are talking about power gain, the maximum oscillation frequency is the frequency that gives us a power gain of 1. So these two figures of merit, the cutoff frequency and the maximum oscillation frequency, is going to give us a view of, well, a limit, I would say, it's going to give us a limit about the frequency that can be used in for a transistor. So what we want now is to get cutoff frequency and maximum oscillation frequency in the range of the terahertz. Okay, if you look at this graph, these are typical graphs about the current gain and power gain. When this current gain reaches the unity, then what we get is the cutoff frequency. If we are discussing about power gain, then when it gets to 1, the maximum oscillation frequency comes to place. Okay, so we are going to discuss the possible cutoff frequency, maximum oscillation frequency that are able to appear. And to put you in the context, to speak about a little state of the art, with the graphene transistors, what the maximum cutoff frequency and the largest maximum oscillation frequency that have been achieved are 427 gigahertz for a 67 sorry graphene field effect transistor. This is the length of the channel, that is the distance between the source and the drain, while the maximum, well, the largest, the highest maximum oscillation frequency is 200 gigahertz. On the other hand, there are currently some materials that are available to be built and to be bought even in shops or so on, in electronic shops, made of indium phosphide and silicon, and they reach very high frequencies as 1 terahertz and 500 gigahertz. But in fact, we expect that the graphene can overpass these limits. So this is why we are still working on graphene and trying to make graphene a material in the terahertz technology. So let's see now how we study this material, this transistor based on the graphene. What we use is a self-consistent model that consists in 2 equations, the Poisson equation and the current continuity equation. We start with an initial guess, that is a distribution of charge around the channel, and then with this charge in the channel, we calculate the electrical field through the Poisson equation, and then with the current continuity equation, we get another charge distribution that we introduce again in the first equation. With this, what we have after some iterations is a solution, a stationary solution that give us the current and the charge distribution in the channel. Okay. Together with the equation that we have already seen, the Poisson equation and the current continuity equation, we solve also the self-heating effect. When you are using a transistor, between the source and the drain there is a current, and sometimes the power dissipated in this graphene cannot spread, cannot go, and then the temperature of the graphene rises. In fact, the rise of the temperature of the graphene makes that the saturation velocity decreases according to the models that we use, and also the current concentration can increase. So the temperature is going to limit the performance of our device. We will see later how much it limits the performance. We use a very simple model with where the temperature rise is proportional to the power dissipated and thermal resistance. Okay, the power dissipated inside the graphene is just the current multiplied by the voltage between the source and the drain. These are typical maps that we get with the with the model that we use. This is the current, the drain current, as a function of the gate voltage and the drain voltage, and we see these kind of maps. For example, if we make a cross section, this dashed blue line would give this line here. This is a transfer curve of the of a graphene transistor, while this dashed green line is an output characteristic. Okay, with the typical kink that can be seen as the drain voltage increases. Apart from the current, as I have said, our model gives us the charge and distribution in the transistor. So the charge at the terminals can be calculated, for example, the charge at the gate and the charge at the drain. So now that we have seen how we get the stationary characteristics, we pass to the high frequency. How do we calculate the high frequency performance? What we do is to apply, well, we choose firstly a bias point, and then over this bias point we apply a small signal that is a voltage, a small voltage, and then what we get is a small current, a small signal current. And if we use the current approximation, what we do is to imagine that we are on this slope of the curve, of the DC curve. And this is what we call the quasi-static approximation. And we use the quasi-static approximation to get the small signal model. Okay, the most important parameters, well, the necessary parameters for the quasi-static model, for the small signal model, are the transconductance, the output conductance at these transcapacitances. In fact, the transconductance and the conductance are the rate of change of the current as a function of the gate voltage and drain voltage, while the transcapacitances are the rate of change of the charges as a function of the voltages. Okay, so this would be, after the simulation, the intrinsic small signal model from the quasi-static approximation with the different transcapacitances and transconductance and output conductance. Okay, so this is a very simple model, and with this we will be able to calculate the radio frequency performance, that is the cutoff frequency at the maximum oscillation frequency. This is the intrinsic model that we have already seen, and apart from this, to calculate the extrinsic model, the model that we can measure, we have to add some parasitic elements that they are going to limit the radio frequency or high frequency performance of our material, of our device, but they are unavoidable. And we will see how they affect the behavior of the device. In particular, we speak about series resistances at each one of the terminals, the gate, the source, and the drain, and also parasitic capacitances between the different terminals. For example, between the gate and the source, between the drain and the source, and between the gate and the drain. Okay, so these 6 parameters are going to be parasitics that are going to limit the performance of our devices. So right now I'm going to try to simulate or show you how to get the typical parameters of a transistor from the experimental work. To do this, we have used a device fabricated at the Chalmers University in Sweden, in Göteborg, by Professor Borovic's research group. You can find all the details of the fabrication in this article of nanoscale device advances published at the beginning of this year. It is a device with a channel length of 500 nanometers. That is the distance between the source and the drain is 500 nanometers, and a width of 15 microns with 2 fingers. And finally, they use as a gate oxide, aluminum oxide of 22 nanometers in thickness. So the first part of everything is to take the transfer curve, and from the transfer curve here the symbols correspond to the measurement, while the line to our simulations. And from this we can get the flat band voltage, that is the point of the minimum conductance. We can get the mobility that goes to 2000, that it is a typical mobility for graphene transistors. And the contact resistance, that is the server resistance at source and drain, and the paddle concentration. The paddle concentration is the minimum carrier concentration in graphene. It is done because of the irregularities across graphene. Once that we have these parameters, we can, with with the output curves, that is the current as a function of the drain voltage, what we get are the density of defects, that it is very low, the density of defects of the interface between the graphene and the different and the substrate. Phonon energy of, the phonon energy is directly related to the saturation velocity, and it gives us how the electrons interact with the phonons, and the thermal resistance that is related to the self-heating effect in transistor. Also, apart from this, we have measurements of the small signal parameters. That is the matrix, the admittance matrix of the device. It is possible to be measured. And with this, we have the gate resistance of 10 ohms and the parasitic capacitances at the input and at the output. This one, the one that is from gate to drain, is 0. It doesn't have a contribution according to our results. Okay, and from this parameter that we have already obtained from this, we can calculate the high frequency performance. And in fact, if you compare the simulated high frequency performance and the symbols that correspond to the measurements, you can see that we get a very, very nice fit between both of them. Okay. In fact, this device is very good in terms that for this channel length, it arrives to 40 gigahertz, that it is quite high. Okay, and this is what we are able to simulate. And another, on the other hand, we have another confirmation that our simulations are good, because if you measure the capacitance, the parasitic capacitances, the corresponding values that we have obtained with our simulation are very close. These signals can be obtained with a device that have been fabricated very similarly to the one that we measure with graphene, but without the graphene layer. So with this open structure, you can measure capacitances that are going to be the parasitic capacitances that appear at the source and drain. So from now on, we have seen until now we have seen how to simulate the device, but now we are going to see how the different parameters affect the performance, the high frequency performance. So if we simulate the maximum oscillation frequency and the cutoff frequency of the device that we have seen that can be fabricated, we get these kind of maps as a function of the gate voltage and the drain voltage. And here you can see that there is a maximum and optimum bias point, where the maximum oscillation frequency and the cutoff frequency are optimal. This corresponds to a bias point where the channel is completely full of electrons, and where there is a depletion of carriers very close to the drain. Okay, this would be the positional on the channel. Here would be the source. Here would be the drain, and you can see that there is a depletion of electrons very close to the drain. So we are going to concentrate in this bias point to see how the different parameters behave, but in fact, using other bias point would give the same results. Okay, so let's start with the contact resistances. We have seen how much the series resistances at the source and the drain affect the maximum oscillation frequency at the cutoff frequency. And you can see that, well, in this graph, the blue and red curves correspond to the series resistance at the source and the drain source, the drain resistance respectively. But if we decrease both of them, they give us our green line. This dashed line would correspond to the value that we have measured. So, actually, I have stated this point that corresponds to the typical values, typical minimum values that can be obtained in graphene technology. Okay, of 100 amps per micron. So you can see that if you reduce contact resistances, you can increase the maximum oscillation frequency from 40 to 48. So there is a slight increase in the maximum oscillation frequency if the contact resistance is reduced. But in fact, if we go to the gate resistance, the maximum oscillation frequency can go from 40 gigahertz to almost 90 gigahertz. So even reducing 1/4 of magnitude the gate resistance, you can obtain a very nice increase of the maximum oscillation frequency. In fact, if you look at the cutoff frequency, you can see that it doesn't affect the cutoff frequency, but it affects a lot the maximum oscillation frequency. We can also compare the influence of the different parasitic capacitances. You can have here 3 curves with 3 colors. In fact, if you look at the maximum oscillation frequency, you can see that the parasitic capacitances are not going to affect this parameter, but the cutoff frequency is slightly affected. For example, if a reduction in the parasitic capacitance at the gate should slightly increase the cutoff frequency from maybe 28 to 30. So the amount of the quantity that we can gain is not very high. We can also discuss about the effect of the self-heating. Here there are the graph that we have already seen with self-heating, where there are some bias, where the maximum oscillation frequency and cutoff frequency are maximum. Okay, instead, if we are not considering self-heating, there will be no maximum, but no absolute maximum. There will be no relative maximum, I'm sorry, but absolute maximum. So the frequency that we are going to achieve is going to be higher for all biases. So if we are able to make the heat go from the device, for example, substituting the substrate by other with a higher thermal conductivity, we are going to get a higher maximum oscillation frequency and the cutoff frequency, that is high frequency performance. and it is going to be limited by the maximum drain voltage that we are able to apply. It's not going to be limited by the self-heating, of course. And finally, we can see how the high frequency performance can be scaled as we reduce the distance between the source and the drain. Okay, as we reduce from 500 nanometers to 50 nanometers, we can see that the cutoff frequency increases up to maybe 500 gigahertz and something like 700 gigahertz for the maximum oscillation frequency. You can compare this with the maximum values that were obtained experimentally in previous research. And you must take into account that these curves are obtained assuming that the thermal resistance and also the series resistances at the terminals as constant. But probably as you get a lower length, these quantities are also going to be scaled. So probably at this point, we will have other limitations. But in fact, if we work with this and with the reduction of the channel length, we probably will be able to get higher. Well, we will be able to work at the terahertz regime, that is 10 to 3 gigahertz. Okay, so thank you very much. I will finish with the conclusions. So we have developed a self-consistent breath diffusion model that includes the self-heating, and from this we can obtain the charge and current stationary curves. That means that we can get the DC curves and compare them with the experiment. From the quasi-static approximation, we can get a small signal model to calculate the high frequency performance of these devices. We have compared this model with measurements of performance of 500 nanometer graphene field effect transistor, and we have studied the different the impact of the different parasitic elements, the series resistances, the parasitic capacitance, and also the self-heating on high frequency performance. Finally, we have seen that the maximum oscillation frequency and cutoff frequency of graphene transistors could reach the terahertz regime. We expect that it could be better than silicon and indium phosphide transistors. But in order to do this, what we have to do is to work on the gate series resistance and the thermal resistance to maximize the high frequency performance. So thank you very much for your attention, and I am currently open to any question that you may pose. Thank you.
Thank you, Dr. Feijoo. You present a great speak. We have one question in the chat. Aníbal Pacheco says, in slides 26 and 27, could you please share your slides 26 and 27, please?
Mm-hmm.
You have shown that RG and CPGD have certain influence on the high frequency figures of merit. These parameters are closely related to the number of gate fingers of the device. There could be a trade-off between RG and CPGD to find either higher FT or higher maximum frequency depending on the application.
Well, first of all,
yes.
No, sorry, I thought that the question was already finished. Well, what it is important is to reduce the gate resistance because this CPGD, we can see that the influence is not that big. So it is much more important to reduce the gate resistance than the capacitance, the parasitic capacitance.
Okay, thank you. He says, do you know why the technology groups only fabricate G-FITs with 2 gate fingers?
Well, because they are easy, but of course there are other approaches.
Okay, thank you. And the other question is, what would be the limitation of increasing, for example, to 40 gate fingers as standard fits?
Well, the main limitation is that this is a prototype, but well, they are done on top of pieces of graphene. So you don't have a very big graphene where you can do whatever you want. You are limited to the size of your piece of graphene that you have on your wafer, on your substrate.
Okay, thank you, Doctor. There is another question. He says, there is an spacer ungated region between source drain with the
Yes,
gate.
there is a space. Yes, I haven't talked about it because I wanted to keep this talk something simpler. But in fact, there is a space between the source and the gate, and the yes, and it is something like 100 nanometers.
Okay, and the question is, does this ungated region with no gate control over the channel has any influence on the RF performance?
Yes, of course, especially. Okay, yeah, probably it has a very big influence on the resistances that at the gate, at the source and the drain. But it's included there.
Okay, and there is another question. What if the device was fabricated on a back gate oxide mesa surrounded by silicon with better heat dissipation properties?
With better heat dissipation properties. Well, I would say that the self-heating effect is not something that the experimental scientists are taking into account right now very seriously. Right now, what they want is just a device that works, and they don't care much about the self-heating. In fact, the temperatures are not being measured. Our model can predict the temperature of the graphene, but still the graphene temperature cannot be measured. So it is difficult to say. I would say that, well, we have a model to calculate the thermal resistance, but in fact it's not, well, we don't trust it too much. We have to work on it.
Okay, thank you. A second question, what about the thermal capacitance? Does it impact on the RF performance?
Well, according to our estimations, the thermal capacitance is very, very, very low, so it doesn't have any impact. We have worked about it. The impact could be that it could affect the high frequency performance, in fact. But what we have seen is that if you are calculating the small signal parameters, what you have to do is to consider that the temperature is constant. If you consider that the capacitance is high, then the temperature would change as you change the voltage, and then the small signal would be affected. It is something that we are working on it, but until now, what I can say is that the capacitance, the thermal capacitance of the transistor doesn't affect too much the high frequency performance.
Okay, thank you. There is another question here. The contact resistance values are in ohms, centimeters, or ohms, micrometers?
Yes, I'm sorry for this. You're right. The resistances must be always in ohms, not ohms per centimeter. But the typical, when you are talking about the contact resistance, you must take into account that you have a width. So the typical value that you give is the multiplication between the contact resistance and the width, because that way you can scale it.
Okay, thank you. Could you perform a simulation in the time domain?
Sure.
Okay, that is the question. Dr. Eloy, do you have some questions?
Just one question. First of all, Dr. Feijoo, for your excellent presentation. It was very, very interesting. Just one question. How the lack of energy band gap in graphene affects high frequency performances?
Well, the lack of gap in graphene affects the possible application in logic, but not at high frequency. What you need at high frequency, let me show you the transfer characteristic. Okay, the blue curve here gives you the transfer characteristic. If it were a band gap, you would have at one side of the curve something like this, but then something that goes to zero. Okay. At high frequency, you are working in this part of the curve, so you don't care about the gap.
Okay.
So it is not that important.
Okay, that's unimportant. Okay, thank you.
Thank you very much.
Thank you, Dr. María Elena.
Thank you, Dr. Eloy. I think there is no more questions, and we are on the time. Dr. Feijoo, thank you very much for your presentation. And we are awarding you this diploma. I'm going to share. Okay. Here we have the diploma. El Instituto Politécnico Nacional, Cátedra Eugenio Méndez de Ocurro, otorga el presente reconocimiento al doctor Pedro Carlos Feijoo Guerro por su participación en el seminario en línea denominado High Frequency and Terahertz Devices and Circuits, Perspectives and Emerging and Advanced Technologies, Part 1, con la conferencia de Theoretical Limits or Radio Frequency Performance of Graphene Field Effect Transistors, llevada a cabo los días 26 y 27 de noviembre de 2020, la técnica al servicio de la patria. Thank you very much, Dr. Feijoo.
Thank you.
Okay.